Okay, so we left off last week, last Wednesday. We were talking about dosages based on weight. And just when we got finished up, we did one example of a dosage based on body surface area. And remember, we were talking, all of these are dosages that are based on the characteristic of the patient. I'll probably never spell out the words body surface area again. The abbreviation is simply BSA. So let's review an example of body surface area here. So just like with the dosages based on weight, the order would be to administer a recommended dose. And this order is going to be every 6 hours. So then we look at either the bottle or look up in a reference book to see what the recommended dosage is for this medication. And we get the recommendation here is 250 to 300 micrograms per meter squared. Now, for body weight, we were based per kilogram, so technically it was mass, not weight. Here, since it's body surface area, it's per meter squared. And this is every 12 hours. Now, just like for weight, we're going to ignore that time frame until the very end of our calculation. We will note, though, that the doctor's orders is to administer it every 6 hours. And just a reminder, one of the things we pointed out is it's okay to give smaller doses more often. That's always okay. There's no risk of overdosing the patient, although sometimes it'll be less effective to give those smaller doses. But going the other direction, giving larger doses less frequently, is risky, and that's something you would have to double check. So anyway, we look at the label here on our supply. And the supply tells us that this is constituted 50 milligrams in 17 milliliters. And of course, just like with dosages based on weight, we need some information from the patient. And let's say our patient here has a body surface area of 0.88 meters squared. The average adult is somewhere around 1.2, 1.3 meters squared of total body surface area. So this is obviously a smaller person or a youth. So we start with the characteristic of the patient, the 0.88 meters squared. And we'll put that over 1 just like we always do to start off our calculations. And we need to get rid of the meters squared, so I'm going to put meters squared on bottom. So up here, we're going to start with the maximum recommendation, which is the 300 micrograms per meter squared. So 300 micrograms per 1 meter squared. So the meters squared are gone, and our units we're in now is micrograms. However, as we look through what we have here, we don't have any other information here with micrograms in it. We do see we have milligrams, so we can do that unit conversion, getting rid of micrograms, so I put those on bottom. Going to milligrams, and we just know this from our standard conversion tables, 1 milligram is 1,000 micrograms. So the micrograms cancel out. But we still need to keep going with this. We have to get rid of the milligrams. We have 50 milligrams in 17 milliliters. So the milligrams cancel out, and now our units are milliliters. And that is a volume. That is something we can administer to our patient. So let's go ahead and we'll multiply the top. 0.88 times 300 times 17 milliliters gives us 4,488 milliliters. Over on bottom, we just have 1 times 1 times 1,000 times 50. That's 50,000. And we need to divide this out. So 4488 divided by 50,000 gives us 0.0897. So we're going to round this to 0.09 milliliters. Now we need to go back and make sure we understand the time frame here. The recommendation was for every 12 hours. The doctor's orders, however, wanted it given more frequency. They wanted it given every 6 hours. So we have to do our titration. Remember, a titration is just a method that allows us to change it. This is for 12 hours. We're going to change this every 6 hours. So we take that calculated dose, 0.09 milliliters, and then remember what it's calculated off of goes on bottom. That's 12 hours that it's calculated off of. And then what we're changing it to goes on top. We're changing it to 6 hours. And also remember that we talked about when we did these titrations, these two units have to be the same, and they are, so they'll cancel out. So we do the 0.09 times 6 divided by 12, gives us 0.045 milliliters, and this is now every 6 hours. So that is half of our solution. Remember, this was calculated off of the maximum recommended amount, so this is the maximum recommended dosage every 6 hours. To find the minimum, we do another titration. So we start with the 0.045 milliliters, which is our max dose. That was calculated using the 300 micrograms per meter squared. And we're going to change it to the minimum dose, which was 250 micrograms per meter squared. Now, once again, these units here are not only important as far as making sure they're the same. Once they're the same, we cancel them out. Now this will be 0.045 times 250 divided by 300, and we get 0.0375 milliliters every 6 hours still. That's most likely going to be rounded to 0.038. So our recommended range is going to be from 0.038 milliliters to 0.045 milliliters every 6 hours. So let's address the big question here. Where does this number come from? The 0.88 meters squared. Well, there are two possibilities. Well, there's actually several possibilities to find body surface area. We're only going to cover two of them, but there are charts. These are charts, that are multivariable or what they would call a contingency table chart, where we might have the height on the side over here. So like, 4'10", 4'11", all the way up to, 5'11", 6'1", and continuing on. And weight along the top. They might have 90 pounds, 100 pounds. Notice height is going to be in 1 or even 2 inch increments. Weight would be 10 or even 20 pound increments along the top. And so you'd find the patient's weight, you'd find the patient's height, and you follow them. That would give you the body surface area for that patient. Very approximate because, again, both the height and the weight are going to be rounded to a nearest number just to save space on the chart. Second option out there is apps. You have downloadable phone apps or on the laptop. even an EMT has a laptop handy pretty much at all times. You can type the information into the app and it'll spit out a body surface area. The ones we're going to use, there's a formula that we'll look at first. And then there is a nomogram. Now, a nomogram is a mechanism that just it's graphics that allow us to line up two numbers, excuse me, and it'll approximate a calculation. Works on very similar characteristics as a slide rule. Most of us have never used an actual mathematical slide rule, but you may have used slide rules for calculating amount of fabric for certain things, or I use them a lot. I used to run a construction company. You'd use a slide rule for calculating the amount of concrete needed for a 4-inch slab or whatever. They're just a very simple calculating device. The nomogram we use doesn't actually use slides, although they do make those that have the little slides that line up. The one that we're going to use, we actually have to line it up with a line or the edge of a piece of paper to read it. So let's start out with the formula. So if we're given for height in centimeters and weight. Now, metric system, we say weight all the time, but we know that what we're really referring to is mass in kilograms. Because kilograms is a unit of mass, not weight. It's just in the medical field, they tend to just keep referring to it as weight because that's what it was used in the standard system. So the formula for the number of square meters of body surface area. So N there is just number, the size. The little sub square meters is saying the units that we get here for the body surface area is going to be in meters squared or square meters. That is equal to the square root of height times weight. Again, that height is in centimeters, that weight is in kilograms, divided by 3,600. So let's use an example here. And for our example, we're going to plug in a patient who comes in with a height of 128 centimeters and a weight 46 kilograms. So we're simply going to plug it into this formula. Body surface area in square meters will be height 128, that's again height in centimeters, times kilograms 46 over 3,600. So when we punch this in the calculator, depending on what model calculator you have, most of your calculators, if they're a two-line display, you'd hit the square root first, then you do 128 times 46 divided by 360. No need to put anything to specify that fraction bar, just doing the division will do it. Then we close our parentheses to tell the calculator we're at the end of the square root. It's going to give us 1.28 square meters. If you have a single line display calculator, you might have to do that a little bit backwards. You would have to do 128 times 46 divided by 3,600, hit equals, and then do the square root on the one-line display calculators. So the next example here, I'm going to get you started, and then I'm going to have you finish this on your own, only because I start with something just a little bit unfair here. So let's say we have a patient here that comes in at 1.48 meters of height and a weight of 90 kilograms. So the warning here is that right there. That's 1.48 meters. Remember, the height that we put into the formula has to be in centimeters. So make that conversion to centimeters first, and then plug that into the formula. I'll give you here about half a minute to plug that in, and then we will go through it. So our body surface area in square meters would be the square root of 1.48 meters is 148 centimeters. So 148 times 90 divided by 3,600. So again, we just punch in square root 148 times 90 divided by 3,600. Close the parentheses, and we get 1.92 meters squared. The second version of the formula is if a patient's statistics are given in standard units. So if our height is in inches and the weight, and this would truly be a weight in the standard system, is in pounds. So here, the body surface area, number of meters, or number of square meters, in meters squared, of course, is the square root of the height in inches now, times the weight now in pounds, divided by 3,131. So you see the only difference in the formula is that constant there. That constant changes actually comes from the conversion factors for centimeters to inches and kilograms to pounds. If I were to take that 3,600 from the previous formula, that is in kilograms. So 1 kilogram is, we use 2.2, but it's actually like 2.208. It continues on. There's a lot more into that. That would get rid of the kilograms, put us into pounds, and then we also get rid of the centimeters going into inches. Well, 1 inch is 2.54 centimeters. That conversion is almost exact. We take our 3,600, it'd be times 2.208 and divided by 2.54. Now, this is not going to come out exact because remember, this conversion is rounded off. But it's going to be really close to that 3,131. We get 3,129.5 about. If we were to take this out to more digits here, we would get the 3,131. So anyway, let's do an example. So for this example, I'm going to look at a patient who has a height of 71 inches and a weight of 168 pounds. So we'll plug it into the formula. The square root of 71 times 168 divided by 3,131. And again, this plugs into the calculator pretty much exactly the same way. Square root of 71 times 168 divided by 3,131. We close the parentheses on our square root. We hit enter. Oh, something did not like that. Oh, I see it. Second square root, 71 times 168 divided by 3,131. Let's try that again. So we're at 1.95 meters squared. I'm going to have you guys try one here in your notes. And once again, I'm going to help you get started because I'm going to do something here again a little bit unfair. We have a patient who's 6 foot 3 inches tall with a weight of 203 pounds. And the one thing I want to help you with to get started here is, again, this 6 foot 3 has to be changed all into inches. And the way we would do that conversion is just take that 6 feet times 12 to make it 72 inches. Add the 3 inches to that. So that is a patient that is 75 inches. So again, from there, height of 75 inches, weight of 203 pounds. I'll give you about half a minute to plug that in the formula, see what you come up with, and we'll double check you here in that in a little bit. Okay, so we'll plug in here the height, 75 inches, times the weight, 203 pounds, divided by 3,131. So on the calculator, square root of 75 times 203 divided by 3,131. Close the parentheses on the square root, and we get 2.21 meters squared. And yes, it is always traditional to round to 2 decimal places on the body surface area. So you can see all of these, I went to the 100th of a square meter for their body surface area. So the next tool, you may have saw me opening it up there as you were working on that problem, is the nomogram. The nomogram, it's a handy, quick tool if you have it with you. But it brings up some issues that I'll point out here as we get started. So the nomogram is actually in your book in 2 spots. It's on page 190, make sure I have the right pages here, 192. And then again on the next page, page 193. I don't know why they felt to do it. The best I can figure it out is on one page, it's a picture of the nomogram, and on the next page, it's the actual nomogram. They both will work exactly the same. One's just a little bit smaller scale than the other. So what the nomogram does, and let me actually just put up a hypothetical patient here that we'll use. A patient with a height of 64 inches and a weight of 115 pounds. So the nomogram allows us, if we don't have the calculator available, because doing a square root without the calculator is not reasonable, not practical to think of. If we don't have that calculator available, we can use this graphic. And so the nomogram here is really 2 charts overlaid. This chart here in the middle, this box, that's not what I meant to do, is a totally separate chart. So the nomogram we're using, really, it only uses these 3 columns on this table. We'll come back and discuss that inlaid box in a little bit. But you can see on the far left here, it is height. And you can either do inches or centimeters, either one. On the other side over here, we're going to use the weight. And that either going to be pounds or kilograms. So here we can mix and match standard units with metric units if we would like to. And then this column here is going to give us that body surface area. Once again, always in square meters. So the example patient we just did was a height of 64 inches. So let me pull up a line here at 64 inches. So the first thing we have to do is find 64. We see here we have 60 and 65, and there are 5 gaps, 5 spaces between them. So that's 5 inches, 5 spaces. Each space is 1 inch. So 64 is going to be right there. On the other side, we need to find the 115 pounds. Well, there's 110 pounds right there. 120 pounds up here, that's 10 pounds, and there's only 2 spaces between them. So that means each space there is 5 pounds. So the 115 is going to be right there. So we'll go from 64, 115, like that. Now I'm going to do some things here to make that line a little bit more visible. First thing I'm going to do is I'm going to change the color so it's red, sticks out a little bit more, and we'll make it a little bit thicker so we can see it better. There we go. We don't want to make it too thick, otherwise it covers up too much of the graph. So now we can see here that line goes through exactly this spot between 1.5 and 1.6. So that would be 1.55 meters squared. Let's jump back over here. So the nomogram gave us 1.55 square meters. Let's double check that with the formula. So our body surface area in square meters is going to be 64 times 115. Now this is in inches and pounds, so the constant down here is 3131. Second square root, oops, we turned off, there we go. Second square root, 64 times 115 divided by 3131, pulls up the square root, and we get 1.53. So you can see here the nomogram is really close to the formula. Close enough. And actually on the nomogram you see it actually did go slightly, actually almost right on the line. Usually it goes slightly below the line, but I must have got my ends just a touch off. Now something to point out on the nomogram, there's actually a couple of things I want to point out. First off is the nomogram uses something called a logarithmic scale. What that means is the size of a space changes from one end of the scale to the other. If I go down to the bottom of the scale here, from here to here is 1 inch, and there's 2 spaces between it. So each of those spaces is half an inch, going from 19 to 19.5 to 20. But if I scroll back up here, from here to here is 5 inches, and it's only one space. That space is 5 inches all by itself. But down here, from here to here is also 5 inches. There's 5 spaces. So each space there is 1 inch. So the value of a space, or the scale on that axis there, changes depending on where we are on the axis. So you can't, if you're one of those people that struggles to figure out scales, the nomogram's not the tool for you, because you're going to have to figure out the scale for every measurement. You can't just figure out the scale once and then apply it everywhere on that axis, because the scale changes. The same is true over here. If I look down at the bottom, from here to here is 2 pounds, and there's 2 spaces. Each space is 1 pound. If I go back up to the top, from here to here is 20 pounds, and there's 2 spaces. Each space is 10 pounds. So again, very different. So make sure you are being very clear on that axis when you use the nomogram. The second limitation here, and this one just always strikes me funny. I don't know why they would do this. Maximum height here on the height axis is 90 inches. Well, 90 inches, is 7'6". We're not going to encounter too many patients that are 7'6" tall. Not unless we're dealing with an NBA team. On the other side over here, however, the weight only goes up to 180 pounds. We're going to deal with a lot of patients that are more than 180 pounds. So if we have a patient that is larger in size, we can handle their height, but we cannot handle their weight with the nomogram. Now, there are other nomograms out there that do go to higher weights and don't go up to as high of a height. This is just the one that's available. This is actually the most common one. If you look up on the internet, this is the version that you will usually pull up when you search for a nomogram for body surface area. So it has those limitations. So if we have a patient who is heavier than 180 pounds, we will have to switch over and use the formula or one of the other methods available to us. So let's do another example here. So we have a patient who has a height of 132 centimeters and a weight of 31 kilograms. Let's go back to the nomogram here. So we're going to change this to 132 centimeters on the left side. So I'm just going to take this end of my line and drag it down to 132. Now again, I have to be careful with my scale. This is 130, this is 140, so that's 10 centimeters. There are 5 spaces between there, so 10 divided by 5 is 2 centimeters per space. So 132 centimeters was the first line above the 130. On the other end, we need to get that at 31 kilograms. So we'll look down here. This is 30, that's 40. That's a 10 kilogram jump. There are 5 spaces between there, so each space is 2 kilograms. So 31 kilograms is between the 30 and that first marking there. So I'm going to take this end here. If I can get a hold of it. There we go. I'm going to pull it down right there between 30 and 32. That's 31. Now let's see where it crosses over here. So again, we have to read the scale on the body surface area here. This is 1 and it's 1.1. So that's 1/10 of a square meter. Between there, we have 5 gaps. So 1/10 divided by 5 is 0.02 or 2/100. So this would be 1, 1.02, 1.04, 1.06 appears to be the approximate body surface area there. The 1.06 meters squared is what my result would be. Let's double check this one with the formula. So 132 times 31, and again, this is metric, so it's going to be over 3,600. And there we go. Second square root. 132 times 31 divided by 3,600. We get 1.066, 1.07 is what it comes out to be. So again, the nomogram and the formula are very, very close. Both of these methods are approximations. There is no exact calculation dealing with body surface area because everybody's different shapes. Look at body weight. We know that there's a difference between muscle tissue and fatty tissue as far as their density. Someone that is 200 pounds of solid muscle is going to be much smaller, more compact than someone who's 200 pounds of fatty tissue. So the person that's solid muscle is going to have a smaller body surface area, even though they might be the same height and weight. So all of these are approximations. So the fact that the nomogram and the formula give us a slightly different answer is not a big deal because it's just approximate. This is all figured in when we look at our recommended dosages. It's figured in there to make sure that we are staying in a safe range regardless of those variations in body types from one to the other. So now let's put this all together and do some examples of calculations of dosages based on body surface area where we have to find the body surface area. So let's look at an example here where the doctor's order is to administer the recommended dose. And again, I'm abbreviating there. Every 4 hours. So the recommendation, when we look up the recommendation for that medication, is 45 to 50 milligrams per square meter of body surface area every 6 hours. So once again, we notice we're going to have a discrepancy in time. The doctor's recommendation is a shorter interval, so it would be a smaller dose than what the book recommendation is. So that's okay. We can give smaller doses more frequently. The label on our supply tells us that this is mixed or constituted at 15 milligrams in 4 milliliters. And now, of course, we need our patient. Let's see with a patient that is 58 inches tall and weighs 92 pounds. So our body surface area here with the square root of 58 times 92. Those are in inches and pounds, so the constant here is 3,131. Square root of 58 times 92 divided by 3,131. Close that up. We're at 1.31 meters squared. There's our body surface area. We come back, we'll start with that 1.31 meters squared to start our calculation. And again, we'll go with the maximum recommended dose, 50 milligrams per meter squared. Canceling out meters squared, so I put that on bottom. 50 milligrams per 1 meter squared, and the meters squared will cancel out. Well, we don't want milligrams either. We're going to get that into milliliters. So we put milligrams on bottom. 15 milligrams in 4 milliliters. Milligrams have canceled out. We will now be in milliliters. So let's go ahead and multiply this out. So we have 1.31 times 50 times 4 gives us 262 milliliters. On bottom, 1 times 15 is just 15. So we'll divide that. Divide by the 15. Give us 17.47 milliliters. Now here again is where we have to remember to bring in our time factor. The recommended dosage was every 6 hours. Doctor wants us to administer the medication every 4 hours. So we have to go back and change that to 4 hours. So we'll start with the 17.47 milliliters. Again, the bottom of our ratio here is what we used, which is the 6 hours. The top is going to be what we want to change it to, which is the 4 hours. So the hours cancel out. 17.47 times 4 divided by 6 gives us 11.65 milliliters, and that's every 4 hours. We need to remember that this is the maximum dosage. We used the larger number when we did that calculation. So now we need to find the minimum dosage. So we start out with that 11.65 milliliter max dosage. That was figured out on the 50 milligrams per square meter. We want to change it to 45. That was calculated on the 50 milligrams per square meter. We're going to change it to 45 milligrams per square meter. So these units are the same again, so they cancel out. Again, they have to be the same or the titration doesn't work. Now we have the 11.65 times 45 divided by 50. Oops, make sure you get the 50 in there. Gives us 10.49. That's milliliters, and the time frame is still every 4 hours. So our recommended range for this medication with this patient is 10.49 milliliters every 4 hours to 11.65 milliliters every 4 hours. So this is a dosage based just on a single shot. We're giving you the medication every 4 hours, all in one large dose each time. But just like our other dosages, these can be given over time. So let's look at the doctor's order, where we're told to administer a recommended dose. Through IV. So through IV means that the dosage is going to be a constant administration over time. We're going to be figuring this out in drops per minute to get our final dosage administered or flow rate administered to the patient. So let's look at the recommendation here. The recommendation given is 75 to 80 milligrams per meter squared every 8 hours. Because this is IV, that 8 hours is going to play a much more prominent role in this calculation. Our label is, this is constituted 25 milligrams in 12 milliliters. And we have a patient who is 144 centimeters and 42 kilograms. And I have to remember to give you the rest of the label here. Our drop factor is given as 18 drops per milliliter. So we look at our patient here, and we're going to do some calculating. Our body surface area in meters squared will be the square root of height of 144 centimeters times weight of 42 kilograms divided by 3,600. Square root 144 times 42 divided by 3,600 is 1.30 meters squared. 1.296, which is going to round up to 1.30, is 2 decimal places. So we'll start our calculation with 1.30 meters squared over 1. Again, we'll use our max dose, 80 milligrams per 1 meter squared. Canceling out the meters squared. We're going to then cancel out the milligrams. 25 milligrams in 12 milliliters, so 25 milligrams on bottom, 12 milliliters on top. Canceling out the milligrams, leaving us in milliliters. Normally, if this were a single shot dose where we're giving the dose once every interval of time, we'd want it in milliliters. We'd be done here. But since this is an IV, we have to go the next step to convert it to drops. So we have 18 drops per milliliter. Milliliters have to go on bottom to cancel them out. So that's 1 milliliter and 18 drops. So the milliliters cancel out. So this first calculation here is going to give us total drops over the interval specified in the recommendation. So we're going to have 1.3 times 80 times 12 times 18. Gives us 22,464 drops. We still have to look at the bottom here, which is 1 times 1 times 25. So that's just 25. And we need to divide that out. So we divide out the 25. We get 898.56 drops. Now we have to go back and bring in the time factor. This was every 8 hours. That's per 8 hours. So now we're going to use that. Come back and look at 898.56 drops. Spread out over an 8-hour interval. And we need to change those hours to minutes. So 1 hour is 60 minutes. So now the hours will cancel out. We're going to have drops per minute, which is the units we want here. So on top, we have 898.56 times 1. That's 898.56 drops. 8 times 60 is 480 minutes. So we'll divide that out. 898.56 divided by 480 gives us 1.872. We round that to 1.87 drops per minute. So this patient is going to get the infuser set at 1.87 drops per minute to infuse that medication. Well, we're down to about half a minute left, so I guess I better give you your homework. Your homework here is on page 196 through 197 in the book. Problems 1 through 19. Calculating body surface area, and then, of course, finding dosages based on body surface area. So now a reminder, on Friday, we're going to do two things. We're going to look at safe dosages. So that means comparing a doctor's recommendation to what is actually recommended as a safe dosage in our reference materials or on the labels of the medication itself. And that'll kind of also be a review for us to review all these dosage calculations, because next Monday is our Unit 3 test. So make sure you're prepped for that. Like I said before, Unit 3 test is where the grades start to drop a little bit, because this is material that you haven't seen in other classes. So with that, I will shut off the recording. You guys have a great day, and hopefully we'll see you all on Friday.